We studied the Fourier series expansion. At here, we would like to see in different point of view. Here, xt signal is defined by cosine omega 0 t. Then we can plot cosine omega 0 t over time domain. Okay, this one is reference 0. Then the signal looks like this one. This is symmetric with respect to y-axis. This is the cosine omega 0 t. But the same signal can be expressed as a complex exponential sum. If we express in the cosine omega 0 t, then a1 equals to 1. It means that the nth harmony n equals to 1. Only one harmony exists. a0 is 0. And a2 is 0. Okay, all the way 0. Only a1 are not 0 in this cosine omega 0 t. If we express that one sum of the complex exponential, then we can express it in that way. In that cases, it is also has the first harmonic only, but we have positive and negative signs at here. So n equals 1 means c1 equals coefficient of the e to the j omega t, so that's the 1.5. N equals minus 1, so n is minus 1 means that this coefficient, it's also 1.5. c minus 1 is also 1.5. n equals 0, c0 is 0. So all the other n's are 0. So that's shown here. So in time domain, we can plot the cosine omega 0 t like that. But in the frequency domain, we can plot that one into two different ways. So this one is frequency. So at this moment, this is dc and omega 0. Actually, this is the first harmonic, second harmonic, and third harmony like that. So only first harmony exist. That's the one. That is a1. Okay, this is this graph. What about this plot? In this case, this is also omega. So this is DC component. How are we gonna plot that one? We can plot the things this way. So 0 and omega 0, 2 omega 0, 3 omega 0, and this is minus omega 0, minus 2 omega 0, and that. It has only omega 0 and minus omega 0. So each one is 1.5. 1.5, like that. So you can plot the spectral domain like this way. This one is a single-sided. It means that only positive frequency exists here. But if we taking the complex exponential, we have a positive and negative frequency. This is called double-sided frequency. Double-sided spectrum. Both of them are the same things. We can plot in this way or this way. If we taking the single-sided, we are using these indexes. You know that the k taking 1 to the positive directions, old index n omega 0 should be positive. But if we taking in this complex exponential terms, ck can take a positive and negative index. So this one is double-sided. So this is the double-sided spectrum, but this one is a single-sided one. So we talk about the three different plot of the xt. This one is just a cosine omega 0 t, so we can plot in the time domain in this way. Time domain has this pattern, but in the frequency domain, if we take in single-sided expression that omega 0 is 1 and all the other frequency component is 0. But if we taking the complex exponential, that's the double-sided, it has positive frequencies is stretched here and negative frequencies exist here. So in the positive frequency, it has only a non-zero value at the omega 0 harmonics. It's a 1.5, and the negative frequency is 1.5. We can plot the spectrum in single-sided or double-sided. So at this moment, you need to know that how to express this one in time domain and the frequency domain. And in frequency domain, we have two different expressions, single-sided or double-sided cases. The next example shows that the impulse train is given like that. Impulse is time shifted every nt. That's plotted over here. So this is delta t. This graph, delta t minus t. Okay. This one is delta t minus 2t minus 3t. This is delta t plus t. Okay, this one. This one is delta t plus 2t like that. This is impulse train. You know what? This signal is periodic. It means that delta x t plus t equals to xt. The period is t. This is the period. So periodic signal can be expressed as a Fourier series expansion. To get the Fourier series expression, we need to calculate the Fourier series coefficient Cn. Cn can be found in this integration, 1 over t. T is the period of the signal. Taking integration over t, we can taking the one period from here to here. This point is minus t over 2. And this point is t over 2. So this period expressed by the period t. So during that period, we need to take integration. We can replace the xt with impulse train. Then 1 over t sigma, and taking integration minus t over 2 to the t over 2, and delta t minus kt times nth harmonic component. We taking this product. But during this period, we will consider only this period. During this period, only single delta function exists here. It means that this delta function is the delta t. Okay, so if we replaced delta t over here, all the other delta functions are not appear in this period. So only t equals 0 is non-zero. Okay, delta function. So we can just safely replace delta t, and k has only 0 value. So we don't care about that one. So by taking integration of this one, we just replace the t with a 0. So this is the integration result. So coefficient are constant 1 over t. Then xt can be expressed by the Fourier series expansion. You know that Fourier series can be expressed by the linear combination of a complex exponential. This one is the nth harmonic, n times omega 0. Okay, the nth harmonic, and the coefficient is constant 1 over t. So the impulse train can be expressed in time domain as an impulse train. Similarly, in the frequency domain, all the coefficient is 1 over t. So it can be expressed in the same way. N means the nth harmony. Okay, nth harmony component are given like that. The next one is the pulse train. Previous we talked about the impulse train. What about pulse train? Pulse train defined like that, but this is also periodic function. Period is t from here. From here to here is a period t. This one is also the periodic signal. Therefore, xt can be expressed as a linear combination of a complex exponential. It's a Fourier series expression is possible due to the periodic property. So to find out the Fourier series coefficient, we have to taking integration over the whole period from here to here. But it has only non-zero value during this period, minus tau over 2 to the tau over 2. So we can taking integration minus tau over 2 to the tau over 2. During this period, xt is 1. So 1 times complex exponential nth harmony should be integrated. To calculate that one, by integrating, it will give these expressions. You can see here, both complex exponential is a complex conjugate. So this part becomes minus 2 times j sine n omega 0 tau over 2. So n is here, omega 0 over 2 is a pi over t period, and tau are given here. So the numerator are given like that, and denominator looks like this one. But denominator omega 0 should be omega 0 times t. Omega 0 times t are equals to 2 pi. So minus j 2 minus 2j is cancelled each other. Then it will give sine n pi t of tau divided by n pi. And if we multiply the tau over t of numerator and multiply that one to make it equal, and then we call this one is a sinc function. Sinc function defined here. The sinc x is sine pi x divided by pi x is called sinc function, sinc x. At here, x equals to 0 is singular, but by taking limitation, limit x goes to 0, you know that sine pi x over pi x. Limit x goes to the 0, then this approach to 1. So that's this one. And also, if x take an integer value, then all those values are 0. So we can represent this part as a sinc function like that. Then we can plot these coefficients along the nth harmony. So this index means that the nth harmony. Last topic is discrete time periodic signal. The period of discrete signal is defined like this way. In this case, n is the period. Let's compare to the continuous domain. In case of continuous domain, t0 was a period, and omega 0 was 2 pi over t0. This was a fundamental frequency, or first harmony component. In the discrete domain, it's the same. The period is n. That's why omega 0 is 2 pi over n. Okay, that's this one. Because this one is the periodic signal, it can be expressed by the Fourier series expansion. But there is some difference to a complex, the continuous signal. In case of continuous signal, complex exponential harmony can be expressed by let this one is a phi. Okay, let this nth harmony omega 0 t is in the continuous domain, but the n is used in the time domain index. I would like to replace this one is a kth harmony. Okay, kth harmony continuous domain expressed in this way. But in the discrete domain, the same complex exponential can be expressed in this way: j times kth harmony n over 2 pi. Okay, n over 2 pi. 2 pi and n times index n. And here t corresponding to n, and the harmonic index number k is here k. Okay, this is complex exponential in the discrete domain, but in the continuous signal, the omega 0 times t is the complex exponential nth harmony. So I write down the nth harmony component at here, but the issue is this one. If we replace n with n plus any integer r times period n. Replace that one here. Then it will give j k times 2 pi over n times n plus n times r. Then it will give e to the j. Okay, I think this is better. Okay. In digital domain, the complex exponential can be given like jk 2 pi over n times n. But at here, okay, if we replace n with n plus r times any integer r times n, then that will give this one, jk, see that, 2 pi over n, see that, n plus rn. Then let's increase the font size. Okay, I would like to explain complex exponential property. In this case, e to the jk 2 pi over n, and it's the same because you know that jk 2 pi over n times r n. Then this n and the numerator n is disappear, so it gives this way. But 2 pi times integer multiple will give unit, so this is a 1. So what does this mean? The meaning, let's think about the range of this k. Range of this k. What kind of value k is possible? In the continuous domain, k taking from 0, plus minus 1, 2, 3, and any value is possible. All integer. But what about here? K. K can taking from 0, 1, 2, all the way up to n minus 1. And what about the next value? It's the same as this one. That's this part says that. So the big difference between continuous and you know what, this is the same. Plus minus is possible. Plus minus is also possible. But the maximum, there is some maximum harmonic index exist in the discrete domain. In discrete domain, the maximum harmonic index n minus 1. Okay, this is the maximum harmonic index because it's repeated here. But in the continuous domain, it goes to the infinity. So there is no limit in continuous domain, but discrete domain is limited up to this point because this one and this one are the same due to this property.